According to the Intergovernmental Panel on Climate Change, global warming refers to the observed and projected long-term increase in Earth's average surface temperature. In other words, increase by 1.6 degrees Celsius due to human activities, particularly the emission of greenhouse gases like carbon dioxide, water vapor, methane, and nitrogen. In 1988, NASA's Goddard Institute for Space Studies presented its findings on climate change to the United States Senate during testimony by Dr. James Hansen, who was the director of the institute at the time. Dr. Hansen's testimony brought significant attention to the issue of global warming and its attribution to human activities, particularly the increase in greenhouse gas emissions. During his testimony, Dr. Hansen emphasized the role of the greenhouse effect in driving global warming. Hansen and his colleagues presented evidence indicating that the observed increase in global temperatures aligned with climate models' predictions of the greenhouse effect. In reports, the prime cause is attributed to human activities and natural factors such as volcanic activity and solar variability. However, before the Industrial Revolution, atmospheric CO2 concentrations remained relatively stable for thousands of years, typically ranging between about 180 to 280 parts per million. Since the late 18th century, atmospheric carbon dioxide concentrations have significantly increased. As of recent years, the concentrations have exceeded 400 ppm. This level is significantly higher than the natural range observed over the past 800,000 years. The continuous rise in carbon dioxide levels since the Industrial Revolution is well documented, with measurements from instruments, such as those at the Mauna Loa Observatory, showing a consistent increase in atmospheric CO2 concentrations. So how does carbon dioxide contribute to climate change or global warming, or now it's called a climate crisis? The sun emits energy in the form of electromagnetic radiation across various wavelengths, frequencies, and energy levels. Upon reaching Earth, a significant portion of the solar radiation is absorbed by the Earth's surface, including land masses and bodies of water. According to Planck's law, objects at a specific temperature emit thermal radiation, and in Earth's case, the absorbed solar energy is re-emitted back into space as infrared radiation. This outgoing radiation carries away heat energy, facilitating the cooling of the Earth. This equilibrium between incoming solar radiation and outgoing infrared radiation is crucial for maintaining stable temperatures and is known as thermal equilibrium or energy balance. Contrary to popular belief, most of the infrared radiation leaving the Earth's surface originates from an altitude several kilometers above the Earth's surface, predominantly within the lower atmosphere known as the troposphere. This phenomenon occurs because the temperature of the outgoing radiation must align with the energy received from the sun, which decreases with altitude. As a result, temperatures further down the surface must increase to maintain this balance. Carbon dioxide molecules present in the atmosphere play a significant role in Earth's energy balance. These molecules can absorb outgoing infrared radiation at specific wavelengths, corresponding to their vibrational modes. Once absorbed, carbon dioxide molecules become excited, temporarily retaining the absorbed energy. However, collisions with other molecules eventually cause the absorbed energy to be re-emitted in all directions, including back toward the Earth's surface. This process, known as the greenhouse effect, traps heat in the Earth's atmosphere, contributing to the warming of the lower atmosphere and surface temperatures, which are conducive to supporting life. However, increased concentrations of greenhouse gases, such as CO2, can have complex effects on Earth's atmosphere, including the stratosphere. The stratosphere primarily receives heat from UV radiation and infrared radiation from the troposphere. With increased carbon dioxide levels, more infrared radiation is absorbed in the lower atmosphere, leaving less available to warm the stratosphere, leading to its cooling. This cooling of the stratosphere serves as a direct indicator of increasing greenhouse gases and their impact on Earth's climate system.
How serious? Very.
ClimateGate.
ClimateGate.
ClimateGate?
ClimateGate is the biggest scandal ever.
In November 2009, a series of hacked emails and documents from the Climatic Research Unit at the University of East Anglia in the United Kingdom were made public. This controversial incident was called ClimateGate.
The climate.
Gates?
Critics of mainstream climate science argue that the emails revealed unethical behavior, scientific misconduct, and attempts to suppress opposing viewpoints among climate scientists. Nevertheless, several investigations conducted by academic institutions, government agencies, and independent panels concluded that there was no evidence of information manipulation. Despite the findings of the investigations, the controversy surrounding ClimateGate contributed to public skepticism about climate science and fueled ongoing debates about the credibility and integrity of climate research. Dr. Willie Soon is an astrophysicist and climate change skeptic. He has published research on solar variation and its potential influence on climate, as well as papers critical of mainstream climate science. According to him, climate change is not strictly human-caused. He points out that the data used in computer modules by the IPCC for estimating global temperature is biased, as he calls carbon dioxide forced warming. For instance, some models have forecasted more warming over the last 150 years than has been observed, and simulations of the last ice age have often shown colder conditions than what is thought to be accurate.
There's your hero. Huh. I never thought he'd really do that.
Another point he makes is that temperature data from weather stations across the United States is contagious due to the urban heat island effect. Let us dive deep into explaining what the urban heat island effect is. The urban heat island effect refers to the phenomenon where urban areas experience higher temperatures compared to their surrounding rural areas. Urban areas often have a higher proportion of heat-absorbing materials, such as asphalt and concrete, compared to rural areas. These materials absorb more solar radiation during the day and release it slowly at night, leading to elevated temperatures. He has suggested that this effect may lead to artificially inflated temperature readings at urban weather stations compared to nearby rural stations, thus biasing temperature records and overestimating the extent of global warming. It is important to understand that climate models rely on input data, known as forcing, which includes atmospheric conditions and concentrations of greenhouse gases, to run their simulations. Uncertainties or biases in these forcing datasets can spread to the model simulations and affect the accuracy. Volcanic eruptions release large amounts of sulfur dioxide and aerosols into the atmosphere, which can temporarily cool the climate by reflecting sunlight back into space and forming sulfate aerosols that scatter sunlight. Nevertheless, the cooling effect from volcanic eruptions is relatively short-lived, typically lasting a few years. However, in 1300, the Earth experienced a major cooling event known as the Little Ice Age, which lasted almost 400 years until 1850. During the Little Ice Age, global temperatures were estimated to have been cooler by about 0.5 to 1 degree Celsius. Recent research has pointed to several volcanic eruptions occurring both before and during this period. One notable eruption occurred around 1257, possibly from Mount Samalas on the island of Lombok, near Mount Rinjani in Indonesia. This eruption is thought to have been one of the most powerful volcanic events in recorded history and may have contributed to a temporary cooling of global temperatures, followed by smaller eruptions in subsequent years. These eruptions, along with the 1452 eruption or the eruption in 1453, are thought to have prevented the climate from fully recovering from the initial cooling, leading to prolonged periods of cooler temperatures. Other volcanic events during the Little Ice Age, such as the eruptions of Billy Mitchell, Winneputina, Mount Parker, Long Island, and Lockie, likely contributed to the overall cooling trend. But it's essential to recognize that the cooling during the Little Ice Age was influenced by various natural factors, such as solar activity, volcanic eruptions, oceanic patterns, and Earth's climate feedback mechanisms rather than a single cause. In contrast, the observed warming trend since the mid-20th century has persisted over several decades and cannot be attributed solely to volcanic activity. Variations in the sun's output, such as changes in solar radiation and sunspot activity, can influence Earth's climate on shorter timescales. However, studies have shown that solar variability has contributed only a small fraction of the observed global warming since the mid-20th century. Direct measurements of solar output have indicated that the sun's activity has not increased significantly during this period, while global temperatures have continued to rise. Our sun undergoes regular cycles of magnetic activity, including the well-known 11-year solar cycle. This solar cycle has two phases, solar maximum and solar minimum. During solar maximum, the number of sunspots increases, and they tend to be larger and more complex in structure. The frequency and intensity of solar flares tend to be higher, leading to enhanced space weather activity, and this phenomenon can cause massive eruptions of plasma and magnetic field from the sun's corona into space. This can lead to an increase in the brightness of the sun. However, the amount of solar radiation reaching the Earth's surface also varies due to factors such as the angle of incidence, atmospheric absorption, and scattering and variations in Earth's distance from the sun throughout the year. All of this can cause global temperature to rise, but is relatively minor. Scientists measure and monitor solar irradiance using instruments such as radiometers and spectrometers both at the Earth's surface and from space-based platforms. A solar minimum, on the other hand, is a period of reduced solar activity in the 11-year solar cycle. However, I want to discuss about the Maunder minimum, which was a period of extremely low solar activity that occurred between roughly 1645 and 1715. The British astronomer Edward Maunder studied historical records of sunspot observations and noted a conspicuous absence of sunspots during this period.
Something's fishy.
The Maunder minimum coincided with part of the Little Ice Age and has been suggested as a potential contributing factor to the cooler temperatures observed during that time. It is important to note that not all solar minima are as extreme or long-lasting as the Maunder minimum.